Welcome to Snoozecast, the podcast designed to help you fall asleep. On Snoozecast, we read excerpts from public domain works and occasionally original stories. New episodes come out every Monday, Wednesday, and Friday. We'd like to thank our listeners. If you enjoy our show, please follow us on social media, write us a review, and also share it with a friend. The best place to listen to us is on our website, snoozecast.com. That way, you can play a single episode and fall asleep without another one automatically playing. This episode is supported by herbal teas made from chamomile, valerian, and lemon balm. Tonight, I'll be reading from Albert Einstein's The Meaning of Relativity. This compilation of Princeton lectures address the consequences of Einstein's theories of relativity. Einstein developed these theories, which became one of the two pillars of modern physics, alongside quantum mechanics. Special relativity applies to elementary particles and their interactions, describing all their physical phenomena, except gravity. General relativity explains the law of gravitation and its relation to other forces of nature. It applies to the cosmological and astrophysical realm. Let's get cozy. Close your eyes. Relax your body into the softness of your bed. Now, take a few deep breaths. The Meaning of Relativity. Lecture 1. Space and Time in Pre-Relativity Physics. The theory of relativity is intimately connected with the theory of space and time. I shall therefore begin with a brief investigation of the origin of our ideas of space and time. Although, in doing so, I know that I introduce a controversial subject. The object of all science, whether natural science or psychology, is to coordinate our experiences and to bring them into a logical system. How are our customary ideas of space and time related to the character of our experiences? The experiences of an individual appear to us arranged in a series of events. In this series, the single events which we remember appear to be ordered according to the criterion of earlier and later, which cannot be analyzed further. There exists, therefore, for the individual, an I time, or subjective time. This in itself is not measurable. I can, indeed, associate numbers with the latter event than with an earlier one, but the nature of this association may be quite arbitrary. This association I can define by means of a clock by comparing the order of events furnished by the clock with the order of the given series of events. We understand by a clock something which provides a series of events which can be counted, and which has other properties of which we shall speak later. By the aid of speech, different individuals can, to a certain extent, compare their experiences. In this way, it is shown that certain sense perception of different individuals correspond to each other, while for other sense perceptions, no such correspondence can be established. We are accustomed to regard as real those sense perceptions which are common to different individuals, and which therefore are, in a measure, impersonal. The natural sciences, and in particular the most fundamental of them, physics, deal with such sense perceptions. The conception of physical bodies, in particular of rigid bodies, is a relatively constant complex of such sense perceptions. A clock is also a body, or a system, in the same sense, with the additional property that the series of events which it counts is formed of elements, all of which can be regarded as equal. The only justification for our concepts and system of concepts is that they serve to represent the complex of our experiences. Beyond this, they have no legitimacy. I am convinced that the philosophers have had a harmful effect upon the progress of scientific thinking in removing certain fundamental concepts from the domain of empiricism, where they are under our control, to the intangible heights of the a priori. For even if it should appear that the universe of ideas cannot be deduced from experience by logical means, but is, in a sense, a creation of the human mind without which no science is possible, nevertheless, this universe of ideas is just as little independent of the nature of our experiences as clothes are of the form of the human body. This is particularly true of our concepts of time and space, which physicists have been obliged by the facts to bring down from the Olympus of the a priori in order to adjust them and put them in a serviceable condition. We now come to our concepts and judgments of space. It is essential here also to pay strict attention to the relation of experience to our concepts. It seems to me that Poincaré clearly recognized the truth in the account he gave in his book. Among all the changes which we can perceive in a rigid body, those are marked by their simplicity, which can be made reversibly by an arbitrary motion of the body. Poincaré calls these changes in position. By means of simple changes in position, we can bring two bodies into contact. The theorems of congruence, fundamental in geometry, have to do with the laws that govern such changes in position. For the concept of space, the following seems essential. We can form new bodies by bringing bodies B, C, up to body A. We say that we continue body A. We can continue body A in such a way that it comes into contact with any other body X. The ensemble of all continuations of body A we can designate as the space of the body A. Then it is true that all bodies are in the space of the arbitrarily chosen body A. In this sense, we cannot speak of space in the abstract, but only of the space belonging to a body A. The Earth's crust plays such a dominant role in our daily life in judging the relative positions of bodies that it has led to an abstract conception of space, which certainly cannot be defended. In order to free ourselves from this fatal error, we shall speak only of bodies of reference, or space of reference. It was only through the theory of general relativity that refinement of these concepts became necessary, as we shall see later. I shall not go into detail concerning those properties of the space of reference which led to our conceiving points as elements of space, and space as a continuum. Nor shall I attempt to analyze further the properties of space which justify the conception of continuous series of points or lines. If these concepts are assumed, together with their relation to be solid bodies of experience, then it is easy to say what we mean by the three-dimensionality of space. To each point, three numbers, x1, x2, x3, coordinates may be associated in such a way that this association is uniquely reciprocal, and that x1, x2, and x3 vary continuously when the point describes a continuous series of points, a line. It is assumed in pre-relativity physics that the laws of the orientation of ideal rigid bodies are consistent with Euclidean geometry. What this means may be expressed as follows. 2 points marked on a rigid body form an interval. Such an interval can be orientated at rest relatively to our space of reference in a multiplicity of ways. If now the points of this space can be referred to coordinates x1, x2, x3 in such a way that the differences of the coordinates delta x1, delta x2, delta x3 of the two ends of the interval furnish the same sum of squares for every orientation of the interval, then the space of reference is called Euclidean and the coordinates Cartesian. It is sufficient indeed to make this assumption in the limit for an infinitely small interval. Involved in this assumption, there are some which are rather less special, to which we must call attention on account of their fundamental significance. In the first place, it is assumed that one can move an ideal rigid body in an arbitrary manner. In the second place, it is assumed that the behavior of ideal rigid bodies towards orientation is independent of the material of the bodies and their changes of position, in the sense that if two intervals can once be brought into coincidence, they can always and everywhere be brought into coincidence. Both of these assumptions, which are of fundamental importance for geometry, and especially for physical measurements, naturally arise from experience. In the theory of general relativity, their validity needs to be assumed only for bodies and spaces of reference which are infinitely small compared to astronomical dimensions. The quantity S we call the length of the interval. In order that this may be uniquely determined, it is necessary to fix arbitrarily the length of a definite interval. For example, we can put it equal to 1 unit of length. Then the lengths of all other intervals may be determined. If we make the xv linearly dependent upon a parameter lambda, we obtain a line which has all the properties of the straight lines of the Euclidean geometry. In particular, it easily follows that by laying off n times the interval s upon a straight line, an interval of length n times s is obtained. A length, therefore, means the result of a measurement carried out along a straight line by means of a unit measuring rod. It has a significance which is independent of the system of coordinates as that of a straight line, as will appear in the sequel. We come now to a train of thought which plays an analogous role in the theories of special and general relativity. We ask the question, besides the Cartesian coordinates which we have used, are there other equivalent coordinates? An interval has a physical meaning which is independent of the choice of coordinates, and so has the spherical surface which we obtain as the locus of the endpoint